Okay, 3-2, logarithmic functions. So specifically, we're going to be talking about logarithmic functions in this section. And one thing to note that we're going to talk about first is they are one-to-one functions. If you remember, one-to-one functions are functions that would pass the horizontal line test, meaning that if they pass the horizontal line test, when you take the inverse of the function, the inverse would also be a function. So we've seen several of our parent functions that have inverses that are also functions, leading us to classify them as one-to-one. So if we recap some of our parent functions and exponentials, we can see that come into play. So first of all, we have f of x equaling x squared. Now, we know that the whole parabola, x squared, would not be a function, or a one-to-one function, but notice the restriction. X is strictly greater than or equal to 0. So when that happens, we only have half of the parabola, or the quadratic. So that allows us to have a one-to-one function wherein we could look at the inverse and it would also be a function. So a quadratic, when restricted, can be one-to-one. The inverse of a quadratic would be the square root function, the square root of x. And again, we put that restriction on it. X has to be strictly greater than or equal to 0. And as I said, this is the square root function. Okay. The next one down, I actually need to make a little adjustment on this. We're going to cross out x to the third, and the inverse is going to be the cube root of x. So the cube root function is the inverse of the cubic, f of x equaling x to the third. X to the third is already a one-to-one function, so it doesn't need any restrictions. And neither does the cube root function. That is an inverse. So if we remember what those look like, here is the cubic function coming down and then the cube root function. Again, they're symmetric, or they're reflected over the line y equals x. Okay, then f of x equaling 2 to the x power. So this is our new exponential that we talked about in 3-1. Now the inverse of an exponential function is a logarithm. So in particular, if we have 2 to the x as an exponential, my inverse would be the log base 2 of x. Okay, and we're going to look at what those graphs look like and all of their characteristics here in just a little bit. Okay, so the inverse provides connection between exponential and logarithmic functions. So exponentials and logarithmic functions are absolutely inverses of each other. However, the first thing we're going to talk about, if you remember in Algebra 2, we can write logarithmic functions as an equivalent exponential function and vice versa. And that's what we're going to look at first, because being able to write them in one form of the other is going to help us to solve and evaluate. So logarithmic form, we're going to start with, we have log base b of x equaling y. So if we want to write this as an equivalent exponential, not the inverse of it, but the equivalent of it, this little trick that I teach is the scorpion tail. You may remember it from a past teacher, or if you had me for Algebra 2. We start at the base. So there's the base of our log. We start at the base with our pencil tip and we head towards the equal sign, looping around until we get to the other side, making a scorpion tail. And the way that we pass those numbers or pass those variables is going to be how we write our exponential function. So if we start at b and we loop toward the y, around, and end at the x, our exponential would be b to the y equals x. And as you can see, that's what we have over here on the other side. B to the y equals x. If we want to go the other way, if we start with an exponential, over here, b to the y equals x. This is my base, b, again. And we're going to do the same exact thing, and the way that we hit the variables or the values, that's the order that we would read the logarithm in. So we would say that the log base b, head toward the equal sign, of x equals y. So log base b of x equals y. And that's what we had in logarithmic form. Just to make it maybe a little more easy to understand, as we use some numbers so that we can really buy into this, let's look at this, let's say 20, let's see, let's say 6 squared equals 36. We know that to be true. We've known that to be true for a long time. So if we were to write that exponential equation as a logarithmic equation, we would start at the base and we would say log base 6, head toward the equal sign, of 36 equals 2. So as a logarithmic function, it is log base 6 of 36 equals 2. And if we wanted to go back in that same direction, back the other way, we would start at the base, head toward the equal sign, and 6 to the second power equals 36. So that's how we would go from a logarithmic function to an exponential and vice versa. So now let's see why we use these. They come in handy when we have to evaluate logarithms. So in example 1, evaluate each of these logarithms. We have the log base 3 of 81. Well, if you notice back up in the algorithms up here, you have 3 parts. You have a b, an x, and a y. And in the exponential, a b, a y, and an x. 3 parts. But with the log base 3 of 81, we only have 2. So when we're trying to find the value of, and we don't know it, we're going to set that equal to x. So if we write this now as an exponential function, we would have 3 to the x equals 81. 3 to the x power equals 81. And so 81 we know is a perfect square. That's 9 times 9. Each of those 9s is 3 times 3, so we could express 81 as 3 to the 4th power. And if that's equivalent to 3 to the x power, we know that x is equal to 4. Now, just a little side note, kind of foreshadowing to what's ahead and coming up. If we saw right off the bat that 81 was 3 to the 4th, look at this, which is not a coincidence. We have log base 3 of 81, which is 3 to the 4th. Notice that our answer was 4, the exponent of the base. So you can kind of think of these as canceling each other out, and the power is what's left as your answer. And through doing this as we do these manipulations, we see why. Okay, letter B, the log base 5 of the square root of 5. Well, we're not sure what that is just looking at it, so we're going to write it as an exponential. Set it equal to x. Let's write this as an exponential. 5 to the x power equals the square root of 5. 5 to the x power, well, since we're in powers, I'm going to write the square root of 5 as 5 to the 1/2. And since the bases are the same, I know that x must equal 1/2, and that would be our value. So once again, no coincidence, the log base 5 of 5 to the 1/2, we see those essentially cancel, and my answer was the exponent. All right, looking at C, I have the log base 7 of 49. If we set that equal to x, I write it as an exponential. 7 to the x equals 49. We know that 49 is 7 squared, so 7 to the x equaling 7 to the, 7 squared, x is equal to 2. And once again, if we recognize that that was log base 7 of 7 squared, we can see that my answer was my exponent. And then log base 2 of 2, setting that equal to 1, 2 to the first equals 2. I'm sorry. Let's set that equal to x. 2 to the x power equals 2 to the first, so x is equal to 1. And again, noticing that log base 2 of 2 to the first, my answer was the exponent. So it's helpful to be able to write logarithms as exponentials when you're trying to find the value. In this gray box, basic properties of logarithms, these are essentially shortcuts. You can always fall back on writing logarithms as exponentials and then seeing what the value is that way. But these 4 bullet points here are shortcuts that we can use to be a little quicker and a little more efficient because they're rules that are always going to carry through. The first one is the log base b of 1 always equals what? So if I think to write that as an exponential, it would be b to the x equals 1. And we know that anytime something to a power equals 1, that exponent had to be 0. So log base b of 1 is 0. Anytime you take the log of something, or the log of 1 with any base, the answer is 0. The next one, the log base b of b is what? Well, if I wrote that as an exponential, setting it equal to x, it would be b to the x equals b to the first. So x equals 1. So in this case, also noticing those are 2 of the same, the bases are the same, the answer is our exponent. And then log base b of b to the x. Once again, the bases are the same, it's just going to be x. And the final one, believe it or not, this last one, even though you see log up here in the exponent, this is an exponential function. It's the log, the exponent is the logarithm, but overall this is an exponential function. So if we wanted to determine the value of this, we could still write it as a logarithm, log, and if I mark this with a question mark, I could say the log base b of what equals the log base b of x. Well, that question mark would have to be x. So this rule, and once again, you may notice the bases are the same of the log and the exponential, and it's just x that remains as our value. Okay. So those are just some shortcuts that you can use when we have some common expressions. Using those then, let's look at the log base 5 of 125. Well, if you recognize that 125 is 5 to the third, it's easy to see that that value is just 3. Then letter B, 12 raised to the log base 12 of 4.7. Once again, the bases are the same, and it cancels. My answer is just 4.7. So those are some ways that we can use those properties to be a little quicker and not need to do any rigorous math. Okay, a logarithm with base 10. You may remember this. It's called a common log. It's often written without the base. So what that means is if I have the log of 3, that is understood to be in base 10. We just don't write it. It's very similar. I compared it in class today. If I gave you this, the square root of 49, you would know that's 7. It's not, there's no 2 that's always written there. It's just understood to be a 2 if there's nothing there. It's the same way with logs. If there's no base written with the common log, log, then the base is understood to be a 10. Okay, then vice versa, well, on the other hand, when we have natural logs, you have a common, or a logarithm with base e called a natural log. This is denoted as ln. You'll see it on the far left side of your calculator, and above it you'll see the e to the x. No coincidence, they are related. Natural logs are always in base e. Both types of logarithms follow the same properties. So what that means is these 4 bullet points up here, these basic properties, also apply to natural logs. Okay. All right, so now let's look at example 3. Evaluate each expression. So as you can see in number 3, there is no base. So we know that this is really log base 10. And we can set it equal to x if we'd like. You can write this as an exponential, or we can try to use some of the properties that we just looked at. So why don't we do that? We can write 1,000th, 0.001, as 1 over 1,000. And I know that 1,000 is 10 to the third, so this would be the same as 1 over 10 to the third. And if I want to put 10 to the third up in the numerator, I'm going to give it a negative exponent, and that would be log of 10 to the negative third. And since I know that there's no base, it was base 10, those cancel, and the value is negative 3. And you always can go to your calculator and type that in, the log of 0.001, and it'll show you negative 3. I would encourage you to do that just to confirm. Letter B, 10 raised to the log of 5. So it does not say it, but this base is 10. So if the bases are the same, my answer will just be 5. So if you forget that principle or that rule and you're not sure, you can always write this exponential as a log. Set it equal to x and start at the base, head toward the equal sign. Log base 10 of x equals log base 10 of 5. Log base 10 of x equals log base 10 of 5. So we know that x has to be 5. Then with the log of 26, this one is actually one that we really need to go to the calculator on. If I wrote it as an exponential, it doesn't get me anywhere. 10 to the x power equals 26. That's not something that I know. So I'm going to go to the calculator on this and just type in the log of 26. And the value that we get is 1.415 if we're rounding to, let's say, 3 decimals. Okay, the log of negative 5. If you set this equal to x, and knowing that this is in base 10, if we wrote that as 10 to the x power equals negative 5, it not only doesn't help me get a value, well, it doesn't help me get a value, but it does help me see that there is no solution here. If you think about it, there is nothing I can plug in for x that will give me a negative number. If I plug in a negative value, all it does is make it a fraction. It doesn't truly change the sign of the number. So you may remember this, you can't take the log, common or natural, of a negative number. Okay. So now let's look at evaluating expressions that have base e. The properties are still going to hold true and operate the same way. So evaluate this first one, that the natural log of e to the 0.73. The thing that gets people confused about this is we think that's the only e there. This is actually not the base that they wrote. The base is not really written. That's natural log base e of e to the 0.73. So the bases would cancel and it would have a value of 0.73. If we look at the next one, the natural log of negative 5, the same holds true. There's no solution. You can't take the log of a negative number. In letter C, we have the e to the natural log of 6 power. Well, that is natural log, can't really write that very well. Natural log base e of 6. So the bases cancel and the value is 6. If you want to double check these because you forget the properties or the principles, you can always go back and rewrite these exponentials as logs or logs as exponentials. Okay? For example, A uses a property. If we just jump back to here for a minute, if we set the natural log of e to the 0.73 power equal to x and we wrote it as an exponential, e to the x would equal e to the 0.73, which is why x is 0.73. So there's our property playing out. In C, e to the natural log of 6, if we wrote this exponential as a logarithm, we would have natural log base e of x equals the natural log base e of 6. And so again, x would have to be 6. And then the natural log of 4, if I wrote this as an exponential, e to what power is 4? That's not really anything anyone would know without a calculator. So when we go to the calculator and type that in, I got x, or the value of the natural log of 4, to be 1.386. Okay. So looking at some of the mechanics on working with these logs, I hope some of those things have come back to you. Now we're going to move on and look at graphs of logarithmic functions. So this is probably brand new to a lot of you, looking at graphs of logarithms. So we can do this a couple of ways, and I'm not going to deny this first way right here is true. You can use the inverse relationship between exponentials and logs to graph them. You absolutely can. And I'll show you how to do that. But I have to say that's not how I'm going to do it most of the time. And so I'll show you both ways. You absolutely decide for yourself. So example 5, we're going to sketch and analyze the graph of each function, describing domain, range, intercepts, asymptotes, and behavior, and increasing or decreasing behavior. So the first thing we're going to graph is the log base 3 of x. So we should understand pretty well, no doubts, f of x is the same as y. So what I'm going to do, and this first way is going to be my way that I do this, I'm going to simply write this log as an equivalent exponential. 3 to the y equals x. So this is going to allow me to just graph this exponential, or graph this log using the exponential form, I guess, as a carrier. So now, here's what's different about this and what some people don't like to do, they'd rather not. I actually pick values for y. I'm going to pick values like 0, 1, 2, and -1. So when I raise 3 to the 0 power, x is 1. 3 to the first is 3. 3 to the second is 9. And 3 to the -1 is 1/3. So I'm going to graph this function, 1, 0, 3, 1, 9, 2, and how about, that was not -1/3, that's +1/3, sorry, 1/3, -1. So here is what a logarithmic function looks like. So this is really the log base 3 of x, even though I wrote it as an exponential and used the exponential format to plug in values. Now, here's what they mean when they say you can use the inverse relationship between exponentials and logs. What you can do also is you can replace, when you find an inverse, you switch x and y, so we can do that. We can state x equals the log base 3 of y, switching x and y. Then solve for y, and to do that, we're going to write it as an exponential. 3 to the x equals y. This is f inverse of x. So what we can do is, now that we get to plug in for x instead of y, which might make you feel more comfortable, I'm going to use the same values. I'm going to plug in 0, 1, 2, and -1. And now I'm going to plug in 3 to the 0 is 1, 3 to the first is 3, 3 squared is 9, and 3 to the -1 is 1/3. So if that's f inverse, then my f of x will be switching those x and y values. So I found the inverse, I put values into the inverse and generated ordered pairs, and now to get the original equation, I'm going to flip them back around. So 0, 1 becomes 1, 0, 1, 3 becomes 3, 1, 2, 9 becomes 9, 2, and negative 1, 1 half becomes 1 half, negative 1. And as you can see, those are the same ordered pairs that I graphed originally. So there's a few more steps. Both ways work. Whatever you like better, it's truly up to you. Okay, we're going to do letter B, the log base 1/2 of x. So if I want to graph this function, I'm going to write this as an exponential. 1/2 to the y power equals x. And I'm going to simply plug in y values in for the exponent. So 0, 1, 2, negative 1, and negative 2. So let's look how this is affecting it. So 1/2 to the 0 is 1. 1/2 to the first is 1/2. 1/2 squared is going to be 1/4. 1/2 to the negative 1 is going to be 2. That negative exponent flips the fraction. And 1/2 to the negative 2 will be like 2 squared, and that's 4. So now let's graph this. So I have 1, 0. I have 1/2, 1. 1/4, 2. I have 2, negative 1, and 4, negative 2. So this is actually our logarithmic function, but this is actually decay. So this is really the log base 1/2 of x. And as you can see, this one goes in a different direction. It's always decreasing, so this is logarithmic decay. And again, you could do the same method. You could write, you could switch x and y, write that as an exponential, and then you would be able to switch those points and plot them. Okay, so now we're going to take, these are essentially two logarithmic parent functions. There are no reflections, there's no stretches, there's no shifting up and down or left and right. So these can be considered parent functions. But now we're going to go to the generic form of these growths and decays for logarithmics and look at the characteristics that make them grow and make them decay. So we have logarithmic growth, log base b of x. It's going to be growth if b is greater than 1, very similar to exponential. So if I have f of x equaling log base 7 of x or log base 3 of x, these are going to be growth. Logarithmic decay, this is where I have a fraction, a positive fraction between 0 and 1. This is going to be decay. So this may be where f of x is equal to the log base 1/4 of x or log base 2/5 of x. Those will be decay. All right, so as we look at these, we're going to look at all of their characteristics. So the domain for growth and decay, their domains are strictly 0 to infinity. You don't have any negatives. The range for both will be negative infinity to infinity. The x-intercept, they both have an x-intercept of 1, 0. They have no y-intercepts. Continuous, yes, they're both continuous. Symmetry, neither of them has symmetry. Extrema, relative or absolute, maximums and minimums, neither of those have extrema. Decreasing. For logarithmic growth, never decreasing, but for logarithmic decay, it decreases from negative infinity to infinity. Increasing, that would always be the case with our growth formula, and never be the case with decay. So end behavior, this is interesting to look at. As x goes to infinity, For growth, f of x goes to infinity. But the other limit we look at is x approaching 0 from the right. F of x is going to go to negative infinity. For decay, the limit, as x approaches infinity, f of x approaches negative infinity. And as x approaches 0 from the right, f of x approaches infinity. So there are some characteristics that we've talked about several times for lots of different parent functions, so they apply to the logarithmic growth and decay. Okay, so now we're going to apply the same techniques to transform these graphs as we did with exponential functions. So we are going to use f of x equaling the log of x to describe the transformation in each function. So what I want to do is look at this as an exponential and get some points with this. And these are just going to be sketches. We know the behavior of these logs and exponentials, so we just need a couple of points to steer us in the right direction. So I'm going to write this as 10 to the y power equals x. And I'm going to generate a couple of points to graph this. So I'm going to plug in for y. I'm going to plug in 0 and 1. So 10 to the 0 is 1, and 10 to the 1 is 10. So these are the points that I have for my parent function. And these three that we're about to do are going to be a transformation of that. So log of x plus 4. This transformation will be 4 to the left. So it's just going to take the parent function and move it 4 to the left. So if I look at those 2 points that I had with the parent function and I move it 4 left, the y values will stay the same, 0 and 1, but the x values will subtract 4. Even though it's x plus 4, remember, if we need to move it to the left, we're going to subtract 4. So 1 minus 4 is negative 3, 10 minus 4 is 6. So I have the ordered pairs negative 3, 0, and 6, 1. 1, 2, 3, 4, 5, 6, 1. There we go. So where I used to have with a logarithm a vertical asymptote, if we take a look back at x equals 0, now I have a vertical asymptote at x equaling negative 4 and an intercept of negative 3, 0. All right, let's look at letter B, the negative log of x minus 5. Okay, so the negative log of x minus 5, the negative will reflect over the x-axis. And the negative 5 will move it 5 down. So there are 2 things that we need to do, and sometimes it matters. It truly matters the order that we do them in, so whether or not it matters, we're always going to think about it. So as we consider the order to do things in, I want you to think about this. When you get up in the morning, think about how you stretch and reflect on your day. You do that first, and then you're going to shift your way into the bathroom, take a shower, brush your teeth, get ready for your day. So we want to reflect and stretch first always, and then do our shifting side to side, up and down after that. Okay, so the first thing we're going to do is our reflection. So if we reflect, how will these points change? And it's over the x-axis. So if it's over the x-axis, then my y values are going to change. So the x's will still remain at 1 and 10, but I reflect over the x, so 0 does stay at 0, but 1 becomes negative 1. Then after that, I have to shift 5 down. So this is my shift. And if I have to shift 5 down, once again, I'm affecting the y values. So my x's stay the same, 1 and 10, but 0 goes to negative 5 and negative 1 goes to negative 6. So I have 1, negative 5, and 10, negative 6. And this is my new function, reflected over the x and shifted down 5. Okay, and the last translation we're going to do, 3 log of x plus 2. So it will have a vertical stretch of 3. And it will shift 2 to the left. So as we look at what those charts, those ordered pairs are going to do, the first thing we do is the stretch of 3. So if it's a vertical stretch of 3, that's going to affect my y values. So my x's will remain at 1 and 10. And my y values I'm going to multiply by 3. 0 times 3 is 0. And 1 times 3 is 3. After I stretch, I'm going to shift 2 to the left, and that will affect my x's. If I go to the left 2, then I'm subtracting 2 from each x value. So my y's stay the same, 0, 3. 1 minus 2 is negative 1, and 10 minus 2 is 8. So I have the ordered pair negative 1, 0, and 8, 3. So this slides it to the left 2 and vertically stretches it up. So the vertical asymptote here is x equals negative 2. Okay, so there are our graphs. We're going to finish with this example, this application problem. So it says the intensity level of a sound measured in decibels can be modeled by d of w equals 10 times the log of w over w sub 0. So first of all, let's point this out. The intensity level of a sound in decibels, that is measured by d of w. Then we have that function, and then it says that w is intensity in watts. So when we're talking about intensity in watts, that's w. And then W naught is this constant, so that never changes. That's not a variable, it's always going to be the same. So A says to describe and analyze the end behavior of the graph of the function. So we're going to look at the limit as W approaches infinity of 10 times the log of W over W sub 0. And actually, let me replace W sub 0 with what we know, 1 times 10 to the negative 12. So the only variable that we have in there is W. And as it gets really, really big, but the bottom denominator stays the same, then that whole value is going to get big, and we're going to multiply it by 10. That is going to go to infinity as well. It's just going to grow and grow and grow. So think about this. What does that mean? As we analyze what that really means, that means as the watts increase, the decibels also increase. So it will get louder and louder as the watts get bigger or higher and higher. Okay, so now we're going to do some calculations. So B says if the intensity of the sound of a person talking loudly is 3.16 times 10 to the negative 8th watts per square meter, so that is W being measured in watts. What is the intensity level of sound in decibels? That's D of W. So we want to find D of W when the wattage is the following. So we're going to just plug that in, 10 times the log of 3.16 times 10 to the negative 8th divided by 1 times 10 to the negative 12th. Okay, and as we plug that in, we're going to get 44.99, which is about 45 decibels. Okay, now we're going to still use that information and look at question C. It says, if the threshold for a certain person with hearing loss is 5 decibels, will a sound with an intensity level of 2.1 times 10 to the negative 12 be audible? So what this means is under 5 decibels, they can't hear it. So let's see if the watts are 2.1 times 10 to the negative 12. Let's see what the decibels are. So decibels, D of W, is equal to 10 times the log of 2.1 times 10 to the negative 12, all over 1 times 10 to the negative 12. When I plug that into the calculator, I get 3.22 decibels. So, will it be audible to that person? No, they will not be able to hear it. It's below 5. Okay, and the last one. It says that sounds in excess of 85 decibels can cause hearing damage. So determine the intensity of a sound with an intensity level of 85 decibels. That is your D of W. So when your result in decibels is 85, what were the watts? So 10 times the log of W over 1 times 10 to the negative 12. And we're going to solve that for W. So we're not going to go to our calculator until the very end. We don't want to do any rounding too early. So the first thing we'll do is divide by 10, and that's 8.5 equaling the log of W over 1 times 10 to the negative 12. Then to get to W, we're going to remember that this is in base 10, that's log base 10. So 10 to the 8.5 power is equal to W times 1 times 10 to the negative 12. And now to solve for W, we're going to multiply by 1 times 10 to the negative 12. So when we put that into the calculator, it will give us back scientific notation, and that is how the wattage is written. So we're going to write it the same way in the same format, and I get 3.1628 times 10 to the negative 4th. Okay, and that concludes the section on logarithmic functions.